Hi there, welcome to this lecture series on matrix algebra. This is lecture 5, part 2. The topic is elementary matrices. In part 1, we introduced the elementary matrices, 3 different types, and what it does if we multiply it to a matrix A on the left. And today we will combine this into the elimination process and using the elementary matrices multiplication to make an A matrix into a reduced row echelon form. So it's slightly different from the reduced row form because it's in the echelon form. We'll define it and we'll discuss it. Okay, let's get started. So we know each of the elementary operations we performed on the A matrix to make it into a reduced row form can be represented by a multiplication of elementary matrix on the left. Okay, so let's now first recall the theorem we had. The theorem says every matrix can be put into reduced form by performing a finite number of elementary operations type 1, 2, and 3. So 1 is multiply a row by a constant, c, that's not 0. And 2 is switching 2 rows. And the 3 will be adding to one row a multiple of another. And then we can replace each of these operations by a multiplication of an elementary matrix on the left. Okay, so this observation immediately transformed the theorem 1 into the following theorem 2, and where we replace the performing blah blah into multiplying with an elementary matrix. Okay, so here's the following theorem. Every matrix can be put into reduced row form by multiplying it on the left by a finite number of elementary matrices. Okay, basically is the same thing as theorem 1. Okay, let's just take an example to see what we do. Okay, let's take an A matrix and let's say we want to put it into reduced row form. So what we do first will be well, this is 0, which is not good, can be serving as a pivot. So we need to switch it. Let's switch it with the third one. So we will be effectively multiplying E13 on A, and then you will get that one. And now let's look at this one and see what I can do to make this guy 0. Well, I see that I can take the first row, multiply by -2 and add on top, and then this will be 0. And then in fact, and it will be looking like this, the final result. Okay, so what we do is to row 1, not, here is to row 2, I add on top of row 1 times -2, which means the elementary matrix will be E2, 1, minus 2. So for on row 2, I add row 1 multiplied by -2. And then finally, I want to make this position 0. What can one do? Well, I could take the second row and multiply by a factor 13/5 and then add on top of the third one, and that will be 0. And you will actually get that. So the elementary matrix we used here would be E3. On the third row, we add the second row, multiply with 13/5. Okay, so then let's call this matrix B. And we see that now it's an or 0 down here in this triangle part, and then easily we can verify this B is in reduced row form. So collecting all the steps, we can write out the B as multiplying A on the left by 3 elementary matrices. So this is the notation here. B equal to A multiply on the left this one, and then multiply on the left this one, and then multiply on the left this one. Okay, so these are written as matrix, elementary matrix applying on top of A. So the order you carry out the performances is now like going to the left. So the one closest to A will be the first product you perform. That's the first operation. And then once this is done, you go one more step to the left and you perform this operation and this product. And then finally you do the last one that will be look like the first matrix here. Okay, so just beware of this ordering is going backwards. Okay, so let's introduce another definition. We call it a reduced row echelon form. It's a step further than a reduced row form. Okay, so the definition is the following. An m by m matrix A is called in reduced row echelon form if all three of the following are true. 1, A is in reduced row form. So this we came across earlier. So this means every row of A has a number of initial zeros strictly greater than the previous row. And number 2, every leading entry of a row of A is 1. So this is not in the simple reduced row form. This is a further restriction we put on. And then number 3, for every leading entry, if you look at the column it is in, then all the other elements in the same column, they are 0. Okay, so again, this is a further restriction we put on here. Okay, and the reason for this definition will become clear very soon, and we'll see it's very easy to solve a system, or it's basically solved a system if A is written like that. Okay, but let's practice recognizing a reduced row echelon form. Okay, let's take 3 examples, and a matrix here, and you see that it is actually an identity matrix. Okay, and this part is 0, so it is a reduced row form. And is it in echelon form? Well, let's single out the leading entries, these 2. So it's 1, and then it satisfies condition 2, and then the condition 3. For each column where this leading entry is in, all other elements are 0. Is that true? Well, for this one, yes, it's true, and for this one, yes, it's true. So the A matrix is in reduced row echelon form. Okay, so now let's look at B. B is a 3 by 4 matrix, and we first see that it is in the reduced row form because this has 2 0 and this one has 4 0, so it's strictly greater than the number of zeros of the previous row. And then let's identify the leading entry. That's this one and that's that one. Okay, and they are 1. So condition 2 is okay. Now let's look at condition 3. So the columns where these are in. So let's look at the first entries. In the first column, are all the other elements zeros? Yes. And then this leading entry is in the 3rd row, and we see all the other elements are 0. So therefore, B is also in reduced row echelon form. Okay, now look at the matrix C. Let's go through. Is it in reduced row form? Well, so this one has 2 0, this 3, and this 4. Yes, it is. Are all the leading rows 1? Yes, they are 1, 1, 1. And now let's look at the last condition. So look at the columns the leading entry is in. So this leading entry is 1 and all the other elements are 0, so that's okay. And this one, and this column, all the other entries are 0. And then the last leading entry 1 here, look at this column. Well, this guy is not 0, so that the condition 3 fails, and therefore C is not in the reduced row echelon form. So we see that we can perform elementary operations on the rows, those 3 types. Then every n by m matrix can be put into reduced row echelon form. So from what we have learned so far, that's exactly what we are performing in order to solve the matrix A. Let's take an example. We see that this matrix here is in reduced row form. We know we can reach that by performing elementary operations. And now we want to further reduce it into reduced row echelon form. So what do we need to do? Well, so basically we want to make the diagonal element to be 1, right? So let's go through that first. So this one is 2. To make it 1 is very simple. I just multiply the first row by half. So meaning I will multiply by this matrix E1 half, and then I'll have first row reduced by half, and the leading entry will be 1. And now let's make this leading entry 1, which is 3 here on the second row. I just need to multiply it by 1/3. So on the second row, I multiply by 1/3, and this is what we get. Now let's go through condition 3. Leading entry, the column where it's in, all the other element needs to be 0. So for this one, it's already okay. Now for this one, that's -3, and we want to make it 0. So what you can do will be add on top of row 1, the row 2 multiply by 3, right? So that is it. Add on top row 1, row 2 multiply by 3, and then this will be 0, and that's what we get. Okay, now the last one, this entry, the column it's in, we need to make the other 2 elements 0. So let's do one at a time. Let's do this one, and what we have to do will be we will need to add on top of row 2 the row 3 multiply by -2/3. So that's what we wrote here. Add on row 2, row 3 multiply by -2/3, and this will be 0. Okay, and then the last element is here. Now to make this 0, we can take row 3, multiply by -2, and add on top of -1, and that's what we did. So row 1, add to row 1 the row 3 times -2, and then that is 0. Okay, now we see that we have a matrix here which is in reduced row echelon form. Okay, so if we call this matrix here B, capital B, then we see that B can be obtained from A, and then multiply it on the left, a sequence of these elementary matrices. That's what we collected. So the first one we did is E1, which is this one, and then the second one is this one, and the third one is this one, and the fourth one is this one, and the last one we did is that one. Okay, so summing up all the observations, now we can state the following. every matrix A can be put in reduced row echelon form, multiplying it on the left by a sequence of elementary matrices. So you might be wondering, what if we multiply matrix A and elementary matrix E on the right instead of on the left? Well, let's take a look. So let's see, like, here's A matrix, and let's take an elementary matrix E. This is obtained from the 3 by 3 identity matrix and switching the second and the third column. Okay? Switching the second and the third row is the same as switching the second and the third column, right? We make that observation. Okay, we can carry out this matrix multiplication, A times E. It's a simple calculation, and you will get this matrix. So you see that the first column is unchanged, but the second and the third column here are switched. So A times E is obtained from A, switching the second and the third column, which is exactly the same elementary operation we performed to obtain the matrix E. So we see that this is similar to the elementary matrix we have talked about, except that if you multiply on the right, then the action is performed on the columns instead of on the rows. Let's take another example. Now we have an elementary matrix and multiply by C here, and we can consider that as multiplying the third column by C. And let's carry out this product, A times this E. Again, it's a simple computation, and you will get this as the final result. And you see that first column, second column unchanged, and the third column here is multiplied by C. So A times E is obtained from A by multiplying the third row with C, which is again the same operation to get that E matrix, the elementary matrix. Okay, so and it's an important and interesting observation that these elementary matrices, if you define the operations on the column instead of on the row, then you can multiply them to the A matrix on the right, and then it does the same operation to the A matrix. Okay, so that is all for today. We'll continue our study in our next lecture. We'll pick up the topic of inverse of a matrix. Okay, so I hope you enjoyed this one, and I'll see you next time.